Hi, let us continue with our discussions about the curtailment of reinforcement. Previously, we mentioned about how do we do the curtailment of reinforcement based on the MED per Z envelope diagram. The one that we mentioned previously was a simplified model where we could separate the amount of reinforcement bar in groups, providing the resistance, ensuring the resistance is always greater than the horizontally shifted MED per Z envelope diagram in the distance of alpha 1. This model here disregards the contributions in terms of the development of tensile stress along the anchorage length. And then, where do we need to stop the reinforcement? It will be at the end of the anchorage length. The one that we discussed previously subdivide the amount of reinforcement bar into 3 different groups. You deal with the first group first. Find the intersection. Add up the second group of the reinforcement plus the anchorage length. Determine where the reinforcement to be stopped. And then find the intersections. Add up the third group of the reinforcement plus the anchorage length at both ends, and this will be the regions where the reinforcement stops. You will do the same for the hogging region. Provide first group of the reinforcement at the end of the shifted MED per Z envelope diagram plus an anchorage length. This is where you can stop your reinforcement. Get the intersections plus the anchorage length, and this is where you stop the reinforcement. Same goes to the third group. You may adopt the principle for the case where you provide reinforcement in 2 groups of reinforcement, or maybe more than 3 groups of the reinforcement. Same principles applied. This model, however, is not seen in Eurocode 2. The one that we see in our Eurocode 2 part 1, in figure 9.2, it looks something like this. This diagram is being reproduced as per indicated here. This model is more complicated, especially when it considers the influence of the anchorage length. Instead of assuming there is no resistance provided by the reinforcement along the anchorage length, this is a more accurate method where you will see the development of the resistance along the anchorage length until it reaches to the full strength of the tensile reinforcement. And then sometimes you see overlapping in terms of the anchorage length, leading to you a more complex resistance profile given by the reinforcement compared to the simplified model that we have discussed previously. There is no overlapping of the lapping length, but sometimes we cannot totally prevent the overlapping of the lapping length, leading to us the actual resistance profile to be more difficult to predict. Since this is the diagram given in the Eurocode, and we use the Eurocode as our ultimate references, it is necessary for us to understand the principles governed by the Eurocode. You see here, there are 3 groups of reinforcement, both at the bottom of the reinforcement and also the top reinforcement. The line here represents the beam. The triangle here represents the support. Assuming this is a continuous beam and this is the end support, this is the internal support. When you analyze a continuous beam, normally you use the moment distribution method, dealing with several combinations of different load cases that give you an envelope bending moment diagram. This bending moment diagram is later being converted into the equivalent tensile force diagram along the beam span. And this envelope tensile force diagram is represented by a formula of MED per Z plus NED. This is another differences between the model given by the Eurocode and the simplified model that we have discussed previously. Our simplified model in our previous videos disregard the Asian loads acting onto a beam member. That means the curve here, it will be only MED per Z. However, the model given by the Eurocode is more thorough, covering a broader applications, where the beam is not only subjected to the lateral load, it may also be subjected to the axial load. And this model takes this into the considerations. To make it simple, you get the envelope bending moment diagram divided by the section modulus of the beam that give you tensile force plus the axial loads acting onto the beam if it is available. If there is no axial loads acting onto the beam, you can consider this equals to 0. That will give you the tensile curve, something like this, as represented by the black line. And then there is a shift of the alpha 1 from the envelope tensile force diagram. The formulas for the alpha 1 in the Eurocode is more thorough as compared to the one that we mentioned previously. It also considers the angle of the shearing. That means this model is applicable for vertical shearing and also the inclined shearing. Let's say now we are dealing with the vertical shearing. That means this will be equals to 0, with the alpha here equals to 90 degrees, leading to the magnitude of the shift of the envelope tensile force. Alpha equals to the formula given here, and through the derivations it is equals to 1.125 D. Bear in mind that the Z used to determine the alpha 1 shall not be taken as the Z for the section modulus. The Z here is referring to the geometrical property of the beam section, whereas the Z here is based on the struct entire model that we use to analyze the response of the beam due to the shear reinforcement. In fact, if you observe this diagram here, we are talking about a horizontal shift of the alpha 1 extending from the original tensile force diagram. Taking this point as a reference, we will see the tensile force that you need to provide due to the moment and also due to the axial loads acting onto the beam equals to MED per Z plus NED. And then there is an additional tensile force due to the shearing, which is as a result of the response in the analogical truss when we analyze the shear reinforcement in a beam. The additional longitudinal force due to the shearing is given here. Plus this additional shearing, it falls just nice on the shifted curve at alpha 1 as per indicated here. This concept is the same as the one that we discussed previously and also the one that you see in Eurocode 2. So coming back to this, the Z here represents the section modulus of the beam section, and then the Z that you use to calculate the alpha 1 comes from the shearing model, which is assumed to be equals to 0.9 times the effective depth from the center of the reinforcement to the center of the reinforcement. Now that you have obtained the shifted tensile force diagram as represented by the red lines. It is now that you start providing the reinforcement. You may adopt the process that we discussed previously. Start with the first group of the reinforcement. You provide this reinforcement here, giving you resistance here. Now, Eurocode is more precise in terms of the stress given along the anchorage length. That means the model given by the Eurocode, you do not need to give an offset of the anchorage length as per the one that indicated here. This is the major difference between the model given by the Eurocode and the model that we discussed previously as the simplified model. In the simplified model, you find the locations where you need to provide the resistance plus an offset of the anchorage length. However, Eurocode takes into considerations the development of the stress along the anchorage length. That means you don't have to offset the anchorage length. Instead, you can start from the end of the shifted tensile force diagram. But you need to make sure that the development of the stress along the anchorage length will provide the resistance always greater than the shifted curve. If the gradient of this anchorage length is greater than this gradient, then your anchorage length can start at the same point. Now, if the gradient here is lower than this one, which gives you the development of the resistance something like this, then you might need to offset a bit in terms of the anchorage length so that it provides sufficient resistance, not less than what is required. And then same principles apply. Theoretically, you can stop your reinforcement here, but normally good practice will require you to go beyond the supports. That's why you extend your reinforcement. And then if you have reinforcement here, go beyond the support here. Make sure it is sufficiently anchorage. You might need to bend the reinforcement, something like this. Now, having the resistance provided here being H, then you may proceed with the second group of the reinforcement. You may find the intersections of the resistance given by the first group of the reinforcement. Start working out the development of the stress and then obtain the resistance areas of the reinforcement. Again, you have to check the angle of the anchorage length against the required. If the resistance angle is stiffer, then you may start at the intersection point. If the angle here is smaller than this, that means if you start here, there is a risk that certain areas will have resistance less than what is required. In this case, you might need to offset a bit in order to make sure the H area here representing the resistance is always greater than what is required. Then you will do the same for the third group of the reinforcement. Now, if you want to compare this model with the previous models that we mentioned in our previous video, under the same tensile force diagram, the one provided by the Eurocode is more accurate, and because of higher level of accuracy, the total amount of reinforcement bar provided will be slightly less than the simplified model. Specifically, we are talking about an additional offset here, which has already been bypassed by the accurate model by the Eurocode 2. Then we look into the hogging moment section. From the bending moment diagram, you will do the conversions by using the moment divided by the section modulus, taking into considerations if there is any axial force acting onto the beam. That will give you the tensile force diagram. Because of the combinations of different types of load cases, we are referring to the envelope tensile force. Then you will need to calculate a shift of alpha 1 horizontally on both sides using the formulas given by the Eurocode in equation 9.2. If we are talking about the vertical shearing, that means the angle of the shearing can be omitted, leading to you the alpha 1s given by this formula. Because of the horizontal shift of this tensile force envelope, the additional resistance given by the shearing has been considered. And then bear in mind that the Z that you use to calculate alpha 1 is referring to 0.9D based on the struct models of the shearing. Not to confuse with the Z, which is the section modulus of the beam here. Now, after you obtain this shifted tensile force envelope diagram, now you're going to provide the reinforcement. Let's say in this case, you have 3 groups of reinforcement. You start with the first group here, taking into account the development of the tensile stress due to the anchorage length. You may choose to start at the same point at the tip of this shifted tensile force diagram, or you may try with a slight offset, as long as you ensure the resistance provided is always greater than what is required. Let's say now the gradient here is less than this. You may try overlapping the anchorage length. The tensile resistance development provided along the anchorage length may be superimposed together, leading to an additional tensile stress along the development length. That's why you see a crooked curve in terms of the resistance provided here as compared to this one. You can see the differences in terms of the resistance profile here. When there is no overlapping in terms of the anchorage length, the development becomes consistent. That gives you a straight angle. In the case that they are overlapping in terms of the anchorage length, the stress developed within the second group of the reinforcement now can help to add up the resistance here. That's why the resistance here end up to be rather crooked here. Therefore, the bottom line here, it will be you will need to try and error and provide the reinforcement in a way that your resistance is always greater than what is required. You may choose to optimize this by minimizing the additional area here in order to maximize the saving of the materials. Now, if you are not that concerned about that limited amount of the saving, probably you can simplify the model a bit, end up with adopting this kind of the model. The implications, it will be you are providing a slightly longer reinforcement bar as compared to those reinforcement bar provided based on the model given by the Eurocode 2. And then from there, at the end of the anchorage length, this is where you're going to stop your reinforcement. And then your curtailment outcome here, you're going to overlay the reinforcement into the beam. and start to indicate where the reinforcement bar should be curtailed. Ultimately, it will end up to be something like this, where certain reinforcement may be curtailed at certain specific locations. Now, same principles applies. This is applicable to 3 groups of reinforcement. Under some circumstances, you may choose to use 2 groups of reinforcement. You will adopt the similar process, only now your resistance diagram will differ slightly. Most likely it will be something like this. This will require you to do the calculations and work out the amount of reinforcement. And before you decide the final detailing of the reinforcement, you need to be careful and make sure the serviceability, durability, and detailing requirements are not compromised. For example, when you work out the top reinforcement bar in the continuous beam, theoretically you may stop all the reinforcement bar here. Since this region has no hogging moment and the top part of the beam here is not subjected to tension. Instead, it is subjected to compression, and just nicely the concrete can withstand the compression. However, due to the practical considerations, you still need at least 2 units of reinforcement in the diameter of 12 mm to be placed on top of the beam. The purpose here is to tie the vertical shear link along the beam. And also, the number of groups of the reinforcement to be provided is often governed by the resistance that can be provided by the reinforcement. Let's say a beam is lightly loaded, where 2 units of H12 rebar is sufficient to withstand the moment and tensile force here. And you know that for a typical beam, industrial practice will have a minimum of 2 H12 rebar. That means there is no point for you to do the curtailment. You cannot reduce the reinforcement further. In this case, my SL, you provide the 2H reinforcement of 12 mm diameter throughout the beam. That's why previously we mentioned the final detailing might not be fully governed by the curtailment that you have calculated. There are also other factors influencing the final detailings of the reinforcement.